Hello. In this presentation, we're going to talk about Anova. First, what is Anova? Anova is a name of a method when we're comparing more than two population means. We have learned how to work with one population mean. Then we learn how to work with two population means. Now, Anova is a method that is going to allow us to compare more than two population means. So what does ANOVA stand for? ANOVA is short for analysis of variance. Now the things that we need to do to get ready for ANOVA is the following list. First, for each sample we enter them into a list. So if you have 3 samples, you're going to use list 1, list 2, and list 3 in your calculator. We identify the number of samples and we're going to call that K. So if you have 4 samples, K will be 4. If you have 5 samples, then K will be 5, and so on and so forth. We're going to find the sum of all sample sizes, and we're going to refer to that as N. Now, different samples, they don't have to have same sizes. They can have same sizes, but they can also be different. So sample 1 could be a sample of 20, sample 2 could be a sample of 15 elements, and sample 3 could be a sample of, 22 elements. So N will be the sum of all sample sizes. Then we're going to set up our null and alternative hypothesis, HO and H1. We're going to use program fval as we did before in order to find critical value f, and it's going to be always right tail test. Then we're going to find compute a test statistic f and p-value p by following the few steps. We're going to go to stat, we're going to go to tests, we're going to find ANOVA and select ANOVA, and then we're going to use the lists like L1, L2, L3, and then when we select all the lists that we have, we press enter. When you're finding the critical value f for ANOVA, the numerator degrees of freedom, it's going to be k minus 1. K is the number of different samples that we have. So if we have 4 samples, the numerator degrees of freedom would be 3. The denominator degrees of freedom is n minus k, where n is the total sample size. So if the total sample size is 35 and k is equal to 5, then the denominator degrees of freedom will be 35 minus 5. Like I said earlier, it's going to be always a right tail test with the right tail area of alpha, where alpha is our significance level. And if alpha is not given, we always use 0.05. Now, how are we going to write the null and alternative hypothesis? The null hypothesis will be that the mean of the population 1 is equal to the mean of population 2 is equal to the mean of population 3, and so on and so forth. So HO is going to be that all the population means are equal. And H1, we're just going to word it that at least one mean is different. Now, ANOVA does not tell us which mean is different. All ANOVA is going to tell us if all the means are equal or at least one of the means is different from the rest. Let's look at the example. We want to use alpha equal to 0.01 and the chart below to test the claim that the mean age of all the students in different colleges are equal or not. So these numbers are randomly selected. We have East LA College, PCC, Mount Sac, Chaffey, Citrus, and Santa Monica College. And the data represents the age of the students that are randomly selected. So in L1, we're going to enter the data for East LA College. For L2, we're going to put the data for PCC. In L3, we're going to put the data for Mount Sac, and so on and so forth. So here we have 6 colleges. That means K is equal to 6. And if I want to figure out N, the total number of sample sizes, we have to find out how many each sample has, add them together, and that would be the value for N. So the null hypothesis is that all 6 means are equal. That's the claim. And the alternative hypothesis would be that at least one of the means is different from the rest. Again, Anova does not tell us which mean is different. Anova is only going to tell us that if all the means are equal, or at least one of the mean is different from the rest. Okay, so K was equal to 6, so the numerator degrees of freedom will be 5. The total sample size is 34, so the denominator degrees of freedom will be 34 minus 6, so it's 28. And like I said, it's going to be always a right tail test. So we use program fval, we follow the steps that we see on the calculator, and we should get the critical value f of 3.754. This is with significance level of 0.01. And again, I emphasize it's always going to be right tail test. Now we're going to use TI. We're going to go to stat, tests, Anova, and then we're going to choose L1, then comma, L2, comma, L3, all the way to L6, and then we hit enter. The computed test statistic will be 1.069. The computed test statistic is F value, and the p-value for this problem is 0.3984. Now we're going to make our conclusion. The computed test statistic is in non-critical region if you're doing a traditional method, or p-value is greater than alpha if you're doing a p-value method. So our conclusion is that HO is valid. Well, if HO is valid, in this case, we are supporting the claim that all the means are equal. I hope this presentation helped you understanding of the concept of Anova and be able to finish your assignments.